So chapter 2 is on the limit. Chapter 2 is the limit. So hopefully you haven't reached your limit yet because we're just starting. But all right. So what we're going to talk about in chapter 2.1 are rates of change and tangent to the curve. So what I want to focus on today is just the average rate of change or the average speed. We've actually encountered this back in other courses. The average, the most common rate of change that we're going to work with is simply the slope. Remember, a rate of change is just how fast it changes between the two variables. So it's the slope. So we start with this dangerous example right here. Dangerous because you can see this guy is dropping metal balls from the Leaning Tower of Pisa. Don't recommend you do that. Probably not safe. Probably get arrested. But we have Galileo here. He did this experiment. He discovered that solid objects dropped from rest, aka not moving, will fall at a distance proportional to the square of the time it has been falling. So if I drop my iPhone, which I will not, let's change it to a poker chip that's up here. Don't know why there's a poker chip in here. I don't know. Interesting, cool. If I drop this, he basically has a function to model how fast it is falling at certain times during its free fall. I'm going to pick that up. All right. So the function or the formula he has is that y denotes the distance fallen in after t seconds, and it's equal to 16t squared. So that 16 is the approximate constant of proportionality. So what is the relationship? So it's just some constant that modifies the output to the function. And this right here is a function of time. So basically, if you were really accurate, and you can just go ahead and I drop this after like 1 second. If you went ahead and looked at 1 second, plugged it in there, that would be how fast it would be falling. Not how fast it would be falling, sorry. It would be the distance fallen. I'm getting ahead of myself there. To figure out how fast we're falling on average is what we're going to have to do down here below. So this will tell us how, oops, didn't mean to erase there. This will tell us how far it's fallen. 16 is dependent on gravity and things like that. So it'll be different on Moon or Venus or things like that. All right, so the average speed or the average rate of change during an interval of time is found by dividing the blank covered by the blank elapsed. So we're going to simply divide the distance, which again is coming from this function up here, by the time elapsed. So that is going to give us a formula for the average speed. The symbols we'll use in this course for change will be, first of all, this triangle, which is the Greek letter delta for difference. So it would be the change in y divided by the change in s. So again, this is the Greek letter delta, which I'll typically just read as change in ... Greek letter. So capital delta is read as change in and then whatever variable. So how do we find the change in y? So this is, to figure out the change in y, you could think about this as the change in distance divided by the change in time. That distance is a function of time, so it'll be, if we have, let's see, the time elapsed, which will just denote the time elapsed as t2 minus t1, or delta, hold on, I made a little mistake here. I should have written t here. This would be the change in time, not s position. So let's correct that. So the change in y divided by the change in t, change in time. So if you have 2 times, it would be a speed t2 minus t1. So then the change in the distance would just be f of t2 minus f of t1. You may also recognize that as y2 minus y1 if you're thinking about rise over run, the slope formula. That's your slope formula. And then in the denominator, we'll have the change in t. Should have written a t there, got distracted. Would be just the t2 minus t1. So to find the average speed, you're literally just going to be using the slope formula. y2 minus y1 over x2 minus x1. In the context of our current situation, though we have not x and y, we're using a function of t, and t is our input. So let's go ahead and figure out if we are visiting somewhere with lots of cliffs, and we see someone on the cliff above us, and he's messing around. So we have like, okay, here's my cliff. I am a terrible artist. There's my cliff. We have a person up here, and he drops a rock, and it is now falling. So that's our context. Oh, it broke loose. Okay. What is the average speed during the first 2 seconds of the fall? So this rock is falling down here, and we want to know after 2 seconds, how fast is it falling? Well, so let's think of part A. What we're giving as our time interval is 0 is less than t is less than 2 during the first 2 seconds of the fall. It is free fall, so it is the function we're going to use is the one that we have above, is 16t squared. To figure out its average speed, we're just going to go ahead and do that. We're going to find the slope. So it'll be f of 2 minus f of 0 divided by 2 minus 0. So this is going to be 16 times 2 squared minus 16 times 0 squared divided by 2. And let's see, this works out to 64 minus 0 over 2, or in this case, it's going to be 32 feet per second. So the average speed of that rock that broke loose, which is the poker chip, which I've already lost anyway. Oh, it's over here. During the first 2 seconds, it averaged speed of 32 feet per second. Any questions on that computation? On part B, though, we're asked the 1 interval second between 1 and 2. But here, before we do that computation, I want you to think about this for a second. So it dropped the first 2 seconds, it averaged 32 feet per second. What about if we were to ignore that first second and just consider between 1 and 2? Do you think the average speed will be faster or slower? We have a vote for faster. We have a vote for slower. Do we have any votes for I'm not sure? Caleb, why do you say faster?
Because things accelerate as they fall.
Things accelerate as we fall, and if you think about, we're ignoring that first second where it was still accelerating. So let's go ahead and verify that, and it will make sense. And again, as we go through this course, always think about the computations, like what do these numbers mean? Does it make sense compared to other results I know? So we're expecting it to be faster. Verify that. Let me give you a moment to do that computation. See if you could do it ahead of me. Find the average speed between 1 and 2 seconds. How many got 48 feet per second? Very good. So again, really all we're finding here is the slope. And again, it is faster because if you think it was falling faster during this second interval, and we just took out some of that first interval where it was slower. Now, here's the last thought I want to leave us for today. What if you're what if you're over here and you're like in a helicopter? So I don't know, this is my helicopter over here. And you have a radar gun right here. There's my attempt at drawing a radar gun. And you want to know how fast the rock is going at this instant. So no longer do you have like a time frame where you could find the slope between two different points. How do you find it out at that instant? And that's the idea that we're going to explore with instantaneous rate of change. And we'll do that in the next class. Does anyone have any questions from today? All right, if you do have questions, feel free to stick around for a few minutes. Otherwise, have a great day, everyone, and I will see you tomorrow. So we're on page 56. We're going to do a couple warm-up problems. Let's actually start with 3. I'll go ahead and start with 3, get myself warmed up out of lunch mode. And then I'll let you guys handle the polynomial one above. So on number 3, we're given this function g of t. It is equal to 2 plus cosine t. And then we're given some interval from 0 to pi. And we want to find the average rate of change. Again, remember that the average rate of change is just simply a slope, average rate of change. It's a slope, and because it has as a slope, it has that formula that's essentially y2 minus y1 over x2 minus x1. Except for instead of using the y's, we're just going to use our standard function notation, where it's in general, just usually denoted with an f. It doesn't matter if it's f or g, but f of t2 minus f of t1. So that's your change in your y's or your rise. And then it's going to be divided by t2 minus t1. That's your change into your x or your change in your independent variable. So of course, what we have right here is not f, but g. And by the way, I'm going to do this a little bit differently than I showed last time because I find sometimes people are more comfortable doing the computations outside of the formula and then plugging the formula in. So if you're one of those, that's fine. So let's go ahead and just kind of take a look that this is t1 is t0, t2 is pi. So in this case, g of pi, or t2, is 2 plus cosine of pi. And of course, cosine of pi, if you think about where you are at on your unit circle, you're at 180 degrees, so you're over here, so the x value is -1. And then if we were to consider g of 0, again, this is t1, this is just simply going to be 2 plus cosine of 0. And at 0, you're at 0 or 360 degrees. I guess we'll say 0 since to reference there. So the cosine value is going to be 1 there. So it's going to then be, let's go ahead and actually carry out these computations. In the first case, it's going to be 1. And in the second case, it's going to be 3. So again, if you're not a fan of doing all the computations inline, you can always just go ahead and do those separately. And then just to figure out the average rate of change, what we'll go ahead and do is just plug it into that formula we described. So that's going to be, I'll just write it like this, I'll say g of pi minus g of 0 divided by pi minus 0. We computed g of pi as 1. We computed g of 0 as 3, so it's 1 minus 3. And then in the denominator, we'll just have pi. So this is -2 over pi. That is the average rate of change. Any questions on the computation there? But again, as we move forward into the course, we want to make sure that we always understand what is this -2 over pi. Yes, it's the slope, but let's also just go ahead and sketch a quick graph of this function and think about it in terms of the visualization or the graph. So, of course, let me just kind of put, okay, remember here that here's pi. Let's go ahead and say no, let me spread this out a little bit. So let's go ahead and here's pi. Over here is 2 pi. And let's say that this is 1 right here. So right here, what I've graphed in black, that right there is cosine of t. That's not g of t because g of t has that addition. Again, if you think about then the addition, all that's going to do is shift it up. So right here now in blue, I have cosine. So is everyone okay with the graphs there? It's just a portion of the cosine, the graph right there in black, and then I shifted it up according to that too. So a little sloppy, but what is this value right here? It is a rate of change. It's the slope. And more specifically, it's the slope of this red line right here. Notice again, what is the slope? Is down 2. I rise -2, and then I run pi. So again, that average rate of change is essentially we draw a line through the points at the endpoints of the given interval. So 0 and pi, we find those points on the graph, draw a line through it, and that the slope of that line is this value. And again, this line right here in red, I'm going to take a sec, and then I'll name it. The reason I took a sec is because it's called the secant. Get it? Sec, secant. Maybe it'll help you remember that little attempt at a joke and a pun. Puns are my humor, so if you don't enjoy them, well, only 13 weeks left in the course. So any questions about this problem right here? Okay, yeah, question? Oh, James, you good. All right, so again, this formula allows us to find the average rate of change. Go ahead and, while I take attendance, slide up and do this one up here in the numerator, where you're given this polynomial function, x squared plus 2x, and you're considering the interval 1 to 3. Haley, Jill, Luke, Raul, Chapel, Destiny, Haley Gardner, Caleb, Sarah, Cadence, Weston, Grace, Josie, Alfred, Savannah, Griffin, Say, Emma, and Soraya, you feeling better today?
Yeah.
Okay, you just had to do the test.
Yeah.
And you got my email with the?
Yeah.
Perfect. Marina, David, Roxana, Corlin, and James. Still awake, James. That's a good sign. All right. Oh. Hey, Griffin. Okay. We just did a warm-up problem, and I'm about to show the work for the second warm-up problem. We're on page 56. All right, so here is the work, at least the computation. I don't have the graph or anything up with this one right now. But when you find the average rate of change, what you should find is that you get an average rate of change of 6. How many got that as their average rate of change? Many of you, very good. Quick little thing, instead of writing like average rate of change each time, you may see me occasionally just write M representing slope, and average just saying this is the average rate of change or average slope. So again, just to maybe save us some writing so much or giving you some shorthand notation, that will go ahead and then help. So does anyone have any questions on that one so far? Yeah, James.
I put 15 over 3 and then I divided.
15 over 3?
Yeah, I did that part, but I didn't do the second.
Okay, so yeah, when you get this right here, this is just the computation for the numerator of the slope. So you could think about this is like my y2 and this is my y1 and my slope. And then my x2 or my x1 and my x2 are the given interval. So just make sure you actually remember to, if you do it separately, to actually do the computation to find the slope and not just the individual y's and x's.
Because what I got, I divided 3 into 15.
Make sure you do the you do the division or the numerator and the denominator separately, because it's acting as a parentheses to keep order of operations. All right, so that's the average rate of change. Let's go ahead to the next page. On the next page, we'll go ahead and summarize what we just talked about in more generality, and we're going to go ahead and set up for the instantaneous rate of change, which I alluded to at the end of last class. So let me go ahead and get to my right spot in the notes just to make sure I say everything that I want to say. Okay, so up here we have just a general function. Let's call this function just f of x. And then on this function, let's just consider, and we're just basically going to kind of set up for something. So what we've been working with is just take 2 points on a function. This right here would be x1. This would be x2. Over here would be f of x1. And then up here would be the associated y value with x2, so f of x2. And then what we did to find the average rate of change is we drew a line through these points. And then this line is going to be the average rate of change. Or excuse me, not that line, but the slope of that line is the average rate of change. Again, what did I call this line earlier? It's the secant line. So this is the setup. Again, you can see that this is just essentially the point right here is just going to be x1 comma f of x1. And this second point up here is the point x2 comma f of x2. You'll find instead of talking about y's, we really talk about it more as outputs to some function. Hence this f of x2 and f of x1 notation. So that's what we could go ahead and fill in this box. The average rate of change of a function with respect to x over some interval x1 and x2. Instead of using t's, we're just using x. So we may just say like the average slope right here, or the or m, or we may say like the m of the secant, either one. So like there's kind of just connect these ideas. I may also say m of the secant is just going to be f of x2 minus f of x1, all of that divided by x2 minus x1. So that's just a summary of what we've already talked about. So let me change up my color here, and let's kind of pose another question. The question I want to pose is, what if we want to know the speed at a given instant? What if we want to know the speed, aka rate of change, at a given instant? If you think about an instant, you don't have 2 times. It's just that was that instant. So there's kind of an issue right here. When we talk about instant, like we can't be working with 2 points, or can we? Well, what we're going to do when we're trying to talk about the instantaneous rate of change, and let me go ahead and underline instant right here, what we're going to do is change up how we're looking at these variables. What we're going to use is we're going to use a letter h, and h represents the distance between x1 and x2. So if I was to visualize what is h, it is this distance between these 2 points. So right there, that distance is h. So again, what is h? It is a distance. Let me ask you now. What is h? It is a distance. Okay, so very good. So what are we going to do with this distance between these 2 points? If you think about, let's suppose we want to know the rate of change at x1. And what we're going to do is we're going to essentially consider points closer and closer to x1. In other words, what we're going to do is we're going to let the distance between an x and another x become so small that you can't even tell it's a different instant. So therefore, it is your instantaneous rate of change. So let's summarize what I just said in a formula, and then we'll work with it, understand it in a few examples. So the quote-unquote here, instantaneous, not average now, but instantaneous rate of change is computed using the formula, and I'm about to show you what that formula is. So I'm going to derive it. So let's see what we started with. We started with f of x2 minus f of x1 divided by x2 minus x1. But what did I say h was? H was a distance. Another way to write a distance is it's just the difference between 2 points. So we'll just do x2 minus x1. We're not going to worry about absolute value because we're going to set up this formula that x2 is your farther point. So if h is the difference between x2 and x1, realize that what we could go ahead and do is solve this and get everything in terms of the same x. So realize that if we know that, let me write this off to the side, this also means that x2 is equal to, let me make sure I write this correctly, x1 plus h. If h is the difference, then we know that if we just add the x1 to both sides, then we end up with x2 equal to x1 plus h. It is the distance between x2 and x1. All right, so the next step in this would be f of x1 plus h. I've substituted x2 with that equality, minus f of x1, and then we divide by x1 plus h minus x1. Zoom in here a little bit. Because this part was x1, or excuse me, x2. But look what happens in the denominator. What we're left with here is just f of x1 plus h minus f of x1 divided by h. Does anyone recognize what this formula or what that equation or expression is called? It's called the difference quotient. So again, maybe your first exposure to this thing right here is referred to as the difference quotient. But realize it's still just a slope. It's still just a slope because it's equal to our slope formula over there. But we're not quite done. So we have that formula and we have to do one other thing with that formula. Before I say it in words, let me just illustrate it up here. Remember, an instant, let's say we want to know the average rate of change at x1. Well, an instant doesn't have 2 points, but we're going to need 2 points to find the slope. So what we're going to do, we're essentially let the distance or the difference between the x and the y disappear. We're going to slide this second point closer and closer to essentially it's the same point. In other words, what we're going to be doing is let the h go to 0. Essentially, we're going to let the distance between the 2 points, or the h, go to 0. So let me write that now. And letting the distance h go to 0. This is our first look at formally the idea of a limit. So again, I'll write it more this way as we progress. But again, to figure out an instant, we're going to let the distance h go to 0, where h is the difference between the 2 points. All right, so let's go ahead and do an example of that on the next page. Instantaneous speed. Find the speed of the falling rock in example 1 at time equal 2 and at time equal 1. Notice the change in our language. Notice we're not talking about an interval or over. We're saying at a specific point, at a specific instant now. So what I'm going to do, let's just focus on this first one. Let's just focus on t equal 1. So this graph right here is going to be, and notice, by the way, the scale. Technically, notice right here is our normal x and y. So the vertex is right here at 0, 0. So notice again, that's 0, 0. 1, 1 is let's see, 1, 1 is about, okay, hold on. So I don't want to say 1, 1 because this function right here is the same one we're using at the beginning. So this is our function f. F is 16 times t squared. So let's consider at 1, technically we're right here at 16. So to figure out the average rate of change, we're going to essentially consider some point after it. And so let's just say this right here, and we're going to, if we were to consider this point right here, we would have a secant line. Right there, that's what we computed back in the first, on the first page. Again, let me remember it. That red line, it has a slope between 1 and 2 is 48 feet per second. So this right here of that red line is 48. So that's the average rate of change. By the way, let me go ahead and switch to a slide. So this will help us out right here. So there I kind of spread it out, but notice down here at the bottom we have 2, here's 1, there's the average rate of change between 1 and 2. And what we're going to do is we're going to just consider points closer and closer to this. So if I were to go ahead and advance one slide, notice now I'm looking at just the distance between, I've let the distance shrink. Right here, let me ask this, for the red line, what was the distance? It was 1. For this blue line here, what is the distance? 0.1. It's just the distance past it. But notice again, we have this secant line. Okay, let's continue. Let's zoom in a little bit. So you can see there's the 2 lines, and then let's introduce another line, and it's kind of hidden by that right there, but you can see right down here at the bottom for that green line, what is the value of h? What is the distance between 0 and some other point? 0.01. So you can see right here is 0.01. We're letting h get smaller and smaller. And if you look at this, essentially, look at how much I have to zoom in to even tell that there's 2 points right there. So essentially, that is the illustration of letting that h go to 0. You're going to get so close to that point that you're concerned about that you're going to end up just saying, you know what? It's so close that I can't even tell the difference between 1 and 1.001 of a second. So that might as well be referred to as the instantaneous rate of change. We're going to just let it become really small. But can we let it go to 0? Did anyone catch? Can we just why can't we just let h go to 0? Did anyone catch why? Luke? Because I don't know if I didn't call it out specifically, but we can't just say h is 0 because there would be a 0 in the denominator, which would then be undefined. So let's kind of summarize what we just have right here. So there right there is our original function. So what we're doing to figure out like the instantaneous rate of change, which I'm going to go ahead and put as this green line right here, what essentially we do is use this formula right here, which I'll just box in. And look at these values. If we let h get smaller and smaller, so basically h is going to 0, and we saw this in the earlier slide right here, what are these values going to? They're going to 32. So m right here is 32. So let's see. So this is basically just doing the computations for us, letting h be smaller and smaller. But again, we want to focus on the pattern that essentially as h gets closer to 0, the slope of the green line is going to approach 32. By the way, this green line, you get a lot of these in Florida. It's referred to as the tangent line. Because there's a lot of sun in Florida, you'll get a tangent line. So you have the secant line. You have an example of a secant line here in red. Again, the secant line is representing the average rate of change. And then if you let h go to 0, you get this tangent line. And again, the tangent line has a slope. Then that slope represents the instantaneous rate of change. We see that the relationship between those two lines explicitly on the next page. So you can see right here, we have 2 points, P and Q. And notice that in gray, we have these secant lines, but we essentially are just letting h go to 0 in order to go get the tangent line. So this distance right here is h, and then all we're doing is let h go to 0 to find the slope of the tangent, or m sub tan. And notice that you can do that coming from the right-hand side, or you can do that coming from the left-hand side. And we'll talk more about left-hand side and right-hand side limits later in this chapter. All right, so let's go ahead and actually do a full computation by ourselves. We'll do number 5. So find the slope of the parabola y equal to x squared at this point 2, 4, and write an equation for the tangent line at that point P. Okay, so what we're going to do is we want to go ahead and find the slope of the secant. So I'll say it like this. Start with a secant. So what we're going to do is compute the m of the secant line. And then we're going to go ahead and use then we're going to let h go to 0. So, I'll explain it like this. So the formula we're going to use is the difference quotient. So f of x1, you could call it x naught, you can just call it x. Let's just call it x, because right now we only have one x value, so that'll be our x, plus h minus f of x over h. But here, x is equal to 2. You have some options. You can plug it in now or you can plug it in later. I'm going to plug it in now. It just makes it a little cleaner in terms of the algebra. So as f of 2 plus h minus f of 2 divided by h. Okay, so I'm going to color code this a little bit. This part I'm going to do in green. And again, depending on your comfort level, you may choose to do this off to the side just so things don't get cluttered. So this right here, this 2 plus h, is going to be plugged into our given function, which is f of x equal to x squared. So this is 2 plus h squared, or 2 plus 4h plus h squared. Again, depending on your comfort level, you may choose to just kind of do it off to the side. So that is just going to be 2 plus 4h plus h squared, remembering to multiply by itself, not just distribute the square. Now let's do f of 2. Again, you may choose to do it off to the side. F of 2 is equal to 2 squared, which is 4. Honestly, you could have found that directly from here. That is f of 2. It's 4. So this is a b minus 4. And then we're going to divide by h. I did make one mistake, though. I rushed and made a mistake. I'll admit to it. Did anyone catch it? Anyone want to call me out? Yeah. So I rushed a little bit. So let me clarify it by adding the additional step. This should have been 2 plus h itself, which should have been a 4 plus 4h. But something you're going to notice, a lot of problems work out nice. Something that kind of made me think about this. It's funny how mistakes cause certain things to appear. What alerted me to that is the fact that these two aren't going to cancel. I've worked enough problems to know like these are supposed to cancel. So when they weren't, I'm like, oh no, I messed up. So again, make sure as you go through things, you notice certain patterns like that. So let's correct this. This should have been a 4. The 4s will cancel, which is what I wanted. And then we're left with 4h plus h squared over h. Dividing both terms by h, we get 4 plus h squared. No h, just 4h. Or 4 plus h, no square. Is everyone okay with where I got that value right there? Okay, so that is not the slope of the tangent line yet. So what we're going to need to do is to find the slope of the tangent. We're going to let h go to 0. And think about this value as you let h, and again, it's kind of abstract right now, but just think about 4 plus h. As you just let h get closer and closer to 0, what is this going to end up just being? It's just going to end up being the 4. So algebra can happen to cancel this out, and we'll talk more about that in the coming days. But the nice part right here, so what we do is then what we get is this giving the m of the tangent as 4. So there's a lot going on in this picture right here. But if you look at this, in black, we have a secant line. We found the secant slope as h plus 4, where h, I mean, if you think about it, if you let h equal to 1, then this would be the point 3, then you would have this as a slope of 5. But what we're concerned about is letting this point slide closer and closer till we get the slope of this tangent line, which indeed is 4. What is the equation of that line? We haven't really done that yet this semester, so let's go ahead and do that. So to get the actual equation, you can use, honestly, whatever method you want. I tend to just default using point slope form. So I will just use y minus some given y point is equal to the slope times x minus some given x point. Then I'll just solve that for y, because really in algebra, in calculus, we're focused more on functions. So we'll typically always solve for y when possible. So again, the given x and y are the points up here. So we have y minus 4 is equal to m, which is 4, times x minus 2. Thank you. The number wasn't coming out of my head. And then we'll solve this for y. So we get y is equal to 4x minus 8 plus 4. So y is equal to 4x minus 4. Which makes sense. If you extend this right down here, you can see that the y-intercept is at 4. The slope is also 4. Excuse me, the y-intercept is minus 4. So notice that each point has its own tangent line too. So this is the tangent line when we're at point 2. If you were to consider like -2 over here, notice its tangent line would be decreasing. Or negative, I should say. The slope would be negative. So start to grab onto ideas like, notice when we're talking about tangent lines, we're talking about a specific point's tangent line. When we're talking about the average rate of change, we're talking about 2 points and then the secant drawn between them. But again, this is the process that we're going to use to go ahead and find the slope of the tangent. Any questions on that process? Quite a few steps, so let me give you a moment to try one yourself. Go ahead and try number 3. Remember, to cube means to multiply something by itself 3 times, so you're going to have a lot of terms here. So you may want to choose just maybe ahead of time, do like f of 2 plus h, which is 2 plus h cubed, which is 2 plus h times 2 plus h times 2 plus h. Yeah, a little bit of a fun algebra problem. Let me give you a moment to try it. You'll need to basically FOIL, then distribute. So. Give it a moment to try, and then if you're having trouble with it, I'll still write it. There's the distribution process with the cube if anyone was having trouble with it. Yeah.
When you first distribute the 2 plus h in parentheses, would it not be 4h?
This should be 4h. Yep, good catch. Good catch. Boy, my arithmetic is off today. Good catch, Caleb. Good analytical eye there. Let's zoom in. So this would be 4. So that would also change this to 8. Is that the one it would change? No, change this one too. So 8, and that is 8h. H squared, 8. Then this would be, no, this would have stayed 4. And then this would have been 4. They're all going to go to 0, which is the nice part. But still, we should still be careful. So that would be 12h and h squared. There should have been 6 of them. Okay. Thanks to your peers, that is now the correct foiling right there. Good analytical, good critical eyes there. Very good. Yep. Nice cancellations of the 8s. So when all is said and done, the slope of the tangent line should be 12, and the associated equation for that tangent line is y equal to 12x minus 16. How many were able to get there? A couple of you, good. This is a tough problem. This is our first exposure to working with some of these ideas. Is there anything I could clarify, though? Yeah.
Can you not simplify the h squared when you have the h underneath?
Can I not simplify the, oh, okay.
You got rid of the h on 12, so you,
Should have been that.
okay.
Yeah, I guess in my mind, I was already canceling them when I didn't care, which I should not do that as the calculus teacher, and I should actually care about every single variable. But yeah, that's a good thing. Yes, to proper cancel, that should have been 12 plus 6h plus h squared, and then those do go away as h goes to 0. So ultimately, what we were looking for was this the equation and then also the slope of the tangent line. So, by the way, pause and just think, does this answer make sense? If you think about the graph of the cubing function, it is just a graph that cuts through the origin like so. Like this right here is the graph. So you have 2, 8. So we're kind of looking at this point right here. And if you think about the rate of change, or let's try to draw the tangent line. That one's pretty good. Right there in blue is y equal to 12x minus 16. So you can go ahead and see the tangent line on the graph. It's basically just tapping that point right there at that instant. And you can see the slope is how fast that graph is changing. Let me ask this question, just to see if the ideas are clicking. Does this function, y equal x cubed, ever have a tangent line whose slope is negative? It does not. Because think about the graph of this function. Is this function ever going to be decreasing? No. It increases on its whole domain, so the tangent lines are going to just be positive. Let me ask this question now. If we were to consider, let's say we were to consider the point 1, 1, right here that I've highlighted and kind of laser pointed in red. Is the slope of the associated tangent line at this point going to have a slope that is greater than 12 or less than 12? Less. Realize it's not increasing as fast there. You could kind of just see, like, if you were to draw it comparatively, it's going to have a slope that looks like this. So the m here is definitely going to be less than 12. So again, start to just think about the big picture of those right there. Anyone have any other questions about 6? All right. 7, we're going to do a problem very similar to this in the next section, so we'll skip 7 for the time being. 8 and 9 is just going to, again, just make sure we're comfortable with the difference between average and instantaneous. So let's go ahead and look at this one right here. So this figure shows the population of fruit flies. Hopefully this problem doesn't bug you. Okay, sorry. It shows how the population P of fruit flies grew in a 50-day experiment. The number of flies was counted at regular intervals, and the counted values were plotted with respect to time t, and the points were joined in a smooth curve. So you can see there's the smooth curve. Find the average growth from day 23 to day 25. What type of line are we going to be looking at here, the secant or the tangent? Secant. Average, again, we're going to be dealing with secant lines. The average, so average means secant. Growth rate is going to be, we're going to be looking at the secant's slope. So you can really see that this is really already kind of done for us. We have the point 23 right here and 45 right there, and we found the associated data. So again, the slope of the secant right here is just going to be the difference in the y's, so 340 minus 150, divided by the change in the time, so 45 minus 23. that works out, again, it's kind of done for us over here, to 8.6 flies per day. But notice we're also looking at 2 points. We're looking at day 23, and we're also looking at day 45. So then the question down below, how fast was the numbers of flies in the population growing on day 23? So are we going to be talking about instantaneous or average here? Instantaneous. We're just giving 1 point and we're saying it's on day 23. So this would be a key word to grab on. The other word that you should also, it doesn't say anything about rate of change in here, but notice it's asking how fast. That's a rate of change. That's a slope. So again, the key word fast, rate of change, slope, all of these should start being connected in our mind as we read through these. So how do we do this? Well, you can see right here, they actually found the tangent line by letting the sequence, the h go to 0. So you can see right here, this was the initial value of h, then they let it get smaller, then smaller, then smaller. And they have for us graphed the tangent line. I think you're going to run into this on the homework where it's just going to give you a graph and it's going to ask you to find the tangent line. My suggestion, I think on the one in the homework, it doesn't line up as nicely on like this point with this point. So just find some lattice points that you can use. So it really doesn't matter. So you can use A and B, you can use A and P, you can use B and P if you need some fuel on that one. Get it? BP? Okay. Let's just finish this up so we can go, right? So you can see right here, they actually computed all of the secant lines. Let's see, what are they doing right here? Okay, here it is. So notice this one right here is getting closer to time equal to 23. And then you could also see kind of what's happening with this right here. These are your slopes. To get the exact value though, we're going to need to just go grab 2 lattice points on the tangent line. So the m of the tangent, let's just use 2 points. What do you guys want to use? A and P, or B and P? A and P. Sounds good. So we'll use A and P. Good choice. I prefer the 0. So let's use A. There's our x1, and there's our y1. And then we'll use P, which is our x2 and our y2. So the slope of the tangent line right there in red is 150 minus 0 divided by 23 minus 14, which works out to about 16.7 flies per day. If you were looking exactly at time 23. Granted, it is increasing because, again, as population increases, they're going to have more breeding opportunities because there's a larger pool. But then it does level out, interestingly. That's an interesting research question. But that is the big thing with secants and tangents. So summary questions. The secant is associated with what type of change? Average. The tangent is associated with what type of change? Instantaneous. Have a great day, everyone. I will see you all tomorrow where we'll pick up with 2.2. So we're going to start today with a quick few review problems, review questions, I should say. So how is the average, keyword here, italicized and now underlined in blue, average rates of change between the 2 points computed? So what do we need to do to find the average rate of change? We need to find what? The slope of the secant. So what we need to do is find the slope of the secant line. So if you're ever asked about the average rate of change, realize rate of change is just a slope that you need to go ahead and find associated with a certain line. Of course, the slope of the secant line, or m sub secant, we found is just going to be f of, and again, if we're talking about change, we'll typically talk about like t1 to t2 as some sort of interval. So it would be f of t2 minus f of t1 divided by t1 minus t2. But again, typically time is always going to be your, well, actually, let me just say this. Time will always be your independent variable. So time will always act as your x, and f of t will always act as your output or your y value. So if we're looking then at number 10, we're asked to give an example where the average rate of change is 0. Go ahead and take about 20 seconds and think about an example where the average rate of change is 0. You could give a function if you want. You could draw a function. But what would be a scenario that you'd run into here? I'm going to answer this with two graphs. So I have one example here, and I'm going to have another example here. The second example is going to get a little long along the x-axis. Must have had a bad breakup along x anyway. 10. Anyone have any idea or kind of just can describe an example that they thought about? Chapel? A constant function is a perfect example. If you think about just any constant function, we'll just take this, say like this one, or that's just positive c. This is an example where the average rate of change indeed is 0. You can see this because if you take any 2 points and draw the secant line literally sits on top of the constant function's line. So again, the secant line is going to be constant, which again, in this case, it is going to be 0. So again, so this red function is f of x is equal to c, and the slope of the secant line here is also going to be 0. Very good. So that's the main function. And again, technically, many functions have a scenario where the average rate of change is 0. Can anyone think to describe one? Let me kind of maybe set this up. Let's suppose we had a function that, let me just throw some numbers on here. So we'll just say this is -2, this is 1. So what if we had a function that looks, let's do this one. Let's take this cubic function right here. Does this function have a scenario where the secant line or a secant line with an average rate of change or with a slope of 0? Yeah. What points would you be considering? So the -2, and what would be the other point? At 1. Realize if you used the points or the interval -2 to 1, look at this secant line. It's a little bit off because, well, drawing is not my expertise. I do my best. But if you look at that, what is the slope of that line? The m here is 0. So is this the only secant line on this graph with a slope of 0? No. Again, the other ones may not be as easy to see, but you can have maybe like this one right here. You can use this one. There's several secant lines where the slope of that secant is 0. So there's 3 different secant lines associated with certain x values, all having a slope of 0. So is there any questions on number 10? Okay. Let's go ahead and look at number 11. How is the instantaneous rate of change at a point on a curve computed? So it's the instantaneous, and again, we can see that's at a point. So what were we trying to find? The slope of the what line? Tangent. So we need to find the slope of the tangent line. So if you remember, what we did last time was we basically took f, and let's call this that point, let's just call that point x. We did f of x plus h minus f of x divided by h. Does anyone remember what h was? It was simply a distance. So it's the distance, some distance past some distance past x, the point we're looking at. So after we kind of simplified that, what did we let h do? We let h just kind of slide to 0. We let the distance go to 0. So what we're going to basically look at more with this idea is we essentially let h go to 0, and we're going to talk about that today in the phrase of the word limit. So you can see right here, we have the LIM, which stands for limit, as h goes to 0. So this little notation that I've just kind of showed over here on the left is the notation. It says, do that computation and then let h go to 0. So that's what we're going to learn more about in this next section. And this right here is literally the computation that'll give you the slope of the tangent line, the m of the tangent line. So let's look at number 12 right now. Give an example where the instantaneous or the tangent line slope is 0. I want to think about this for a sec. Go and sketch maybe an example or give a function. And then anyone have any ideas? Describe what is happening when the instantaneous rate of change is 0. Very important idea right here. The sooner you get this, the sooner you understand about 10 of the lessons in this course.
Just like a parabola.
So let's consider a parabola. Okay, so let's say we have this one right here. Is this one fun? Well, let's actually make it a parabola. So let's say that's parabolic. Okay, that's terrible. My OCD a little bit's kicking in there. That's a little better. Thanks, Griffin. Okay, so I have my parabola. What about it?
Like at the very top.
At the very top. I like how you said that, at the very top, because you can see right here, let's get that on the actual graph. This is a tangent line whose slope is 0. So what do you notice is happening when the tangent line is 0? We have a maximum. So hold on to this idea that we have a max when m of the tangent is 0. Very important idea. That is basically a whole subset of calculus called optimization problems. Where do I make the most money? What shape should I make my product? When should I give the patient more medicine? Of course, can you have a function with more than one horizontal tangent? Yeah, we could take maybe a cubic one that looks like this one right here. So you can see there's a horizontal tangent there. There's also a horizontal tangent right down here. So notice again, where there's a horizontal tangent, you may also have a minimum value. So then to figure that out, we have to kind of talk about what happens in between. So we have this idea or this phrase where I've seen maybe students who've taken calculus before will kind of maybe loosely describe the tangent as a line that only touches the graph once. Can a tangent touch the graph more than once? Careful with that. It can, because this extends, but the tangent is always going to be associated with a certain point. Each point has its own tangent line. That tangent line is telling you if the graph is increasing, decreasing, or changing. So notice here, when the tangent line has a slope of 0, it is actually changing from increasing to decreasing. So that's something we're going to explore more in chapter 3, but just want to go ahead and kind of start planting those seeds, sowing those seeds, and we'll see them come to harvest later in this semester.